So, all right, hello everyone. It's the fourth lecture, and the focus of today is going to be about the concept of symmetry in Noether's theorem. So, this is kind of coming off the back of our first lecture about symmetry. One person wasn't there. I'll just say it. The idea of a symmetry is a transformation that leaves some particular thing invariant. So before, you had the idea of like a shape being symmetric, and what's being preserved is sort of the shape and connections between the vertices of that thing. But in general, it could be something like, well, what we're going to see today. So I want to start with first few things before we get into that. So I'm going to use this term called configuration space. So configuration space is just you can think of it as the space of positions of your system. So if you had one particle, the configuration space would just be 3D space. This particle would just be moving through X, Y, Z, whatever. But if you have multiple particles, then you get more and more copies of this thing. So, like we talked about before, for n particles, you have 3n degrees of freedom. So then your configuration space would be 3n dimensional. Okay? Is that a marker? Okay. Right. So the space that all of these QIs live in, if you kind of take it together as a sort of vector, not necessarily a spatial vector, but more like a list of numbers, then this lives in the configuration space. Right. So then the idea of classical mechanics, with whatever formalism you're using, is that given the state of the system in this sort of configuration space, if you know where its position is in this thing, and you also know at that instant what the velocity is, these laws of physics, be it Newtonian mechanics or Lagrangian mechanics or whatever, they're going to tell you the whole evolution of the system through all time. And you can also go backwards. So, I think there's another thing I wanted to mention. Yeah, another way you can view the degrees of freedom is by saying, at one instant, there is not necessarily a relation between the position and the velocity of a particle. So you might want to consider Q and Q dot to be independent. So you might find this confusing, you might not. It's kind of just a difference in perspectives. But what might be alarming is that when you consider these as independent, your degrees of freedom double. Okay? But what saves you is that you get these additional 3n equations relating Q and Q dot, which is the basic relation that Q dot is the time derivative of Q. So before I put this as a definition, but if you consider these to be independent, then this is kind of a relation. Okay? So the idea is that we have 6n degrees of freedom. We get 3n equations from this. We also get 3n equations from the Euler-Lagrange equations. I forgot the So this gives you another 3n equations. So in total, you have 6n equations, 6n degrees of freedom, which means the whole system should be solved. Okay? The last thing that I'll just talk about conceptually is that at the very end of last lecture, we talked about using Lagrangian mechanics for a simple harmonic oscillator, so something like a mass on a spring. And that's actually particularly useful because you can apply it to more general situations. So if you have a more general potential energy, so you have some u of x, let's say looks like this, then the idea is that there's actually a stable equilibrium in this area, so around this point. And so if your particle is kind of situated near this point, maybe it's just a very little distance away, you can approximate your physical system as a simple harmonic oscillator. And you're basically approximating your potential energy as some kind of quadratic. So the way you would do that is through matching the second derivative of this.
A sort of Taylor series?
Yeah, basically. It is a Taylor series, and because this is at equilibrium, so let me do this. So you get the potential at equilibrium, then the first derivative at equilibrium times this, plus 1/2 the second derivative at equilibrium times this squared. But since it's at equilibrium, the force is 0, right? So this first derivative will be 0. So what you get is this. This is some constant, which you associate with the spring constant of the system. And then this part gives you the quadratic potential, which is characteristic of a harmonic oscillator. Okay, so the idea is that this is true for x very close to x naught. So you can use your sort of Lagrangian formalism and whatever to talk about like small oscillations around equilibrium. Okay. All right. Now we can get to the main stuff. Those were kind of just small points. So today we want to talk about transformations that we can do to our configuration space that will preserve the action. So action is what we talked about yesterday. It is the integral of Lagrangian over time. And the idea is that if we have some sort of trajectory, and then we perform some transformation of the trajectory everywhere, we want such a transformation that will leave the action invariant. So if this is Q, and we make some transformation that goes from Q of t to Q prime of t, and then Q dot to Q dot prime, which usually will just be the time derivative of this. Then we would get a new action, potentially. But we want transformation such that this is actually the same as the original action.
And what is the difference between Q prime and Q dot again?
Q prime, oh, right, yeah. So prime I'm not using here to denote a derivative. I'm just saying it's the new one.
Sure, okay.
Yeah. So, right, maybe an easier way to convey this is that our old action, we took in q, and then our new action, we take in q prime, this is the new trajectory, but we want them to be the same. Okay? So, when I talked about symmetry transformations as being transformations that preserve some sort of thing, the thing that's being preserved here is the action. So these transformations will be a symmetry group. Okay. And I want to specify this doesn't necessarily have to be true just for the sort of physical trajectories, the ones that will actually happen from the laws of physics. We're saying that we want this to be true no matter the trajectory we consider. Okay? So what that then means is that, let's say our action is sort of rotationally invariant. If we rotated the whole trajectory at once, or just rotate the whole space at once, if that preserves the action, then basically what we're saying is that, let's say our origin is here. If we rotate the trajectory so that it's like that, or something like that, the new trajectory is the solution to the Lagrange equations if these were our initial and final conditions, because these will now minimize the action. And that's basically because the change in action between here and here was 0.
So that would be like taking a satellite in orbit of Earth and moving it, but maintaining it at an equal radius and equal velocity.
Yeah, and not just equal velocity, but equal speed, but you're rotating the velocity.
Yeah.
Okay, so that's an example that I'll come to during one segue. Yeah. Actually, maybe we should do that now. So let's do a simple 2D example. So we have a two-dimensional free particle. The free particle again means that there's no forces, no potential energies. And so the Lagrangian we said before is this.
Can I have a box of tissues?
Yeah, okay.
Thank you very much. Sorry about you guys.
All right. What we can also do is express this in polar coordinates. And so you could substitute in the polar coordinates, do the whole transformation, and that takes a bit of time. But what you could also consider is that if you have some particle moving some velocity, part of it is radially outward, and part of it is perpendicular to that. So it's kind of going angularly. And so the radial part will be r dot, so we get this. And the angular part will be r times theta dot. So this is like the v equals r omega. So that would be this. And we could then expand that. Okay. So our two coordinates are r and theta. If I instantaneously rotate the system by some angle, what happens to r and what happens to theta?
R remains constant and theta varies.
Right. And so let's say I do a rotation by some fixed angle, let's call it epsilon. So r goes to r. What does theta go to?
Epsilon. Or theta plus epsilon.
Yeah.
Yeah.
Okay. What about r dot?
Just R dot.
And theta dot?
That would remain constant as well, right?
Yeah.
Yeah.
Because this transformation is not time dependent. So when I take the time derivative of this epsilon, it does not change over time.
Is there an R dot? From what I understand, anything with a dot above it is the derivative of the first thing, right?
Yeah.
So would there be one if it's just done instantly?
Well, I think what he
Yes.
means is that the speed is constant,
Okay.
right? Like if you take something and you keep it in the same place, it's still going to have the same
Okay.
speed.
So what's happening is that when we rotate the particle instantaneously, we're rotating the position, because at that instant, it is also moving, right?
Oh,
That's the idea of having
okay.
the derivative, the time derivative of it, right? And then when we rotate it, we rotate its position, we also rotate its velocity. So you can kind of think of it in a sort of inverse way, that instead of moving the particle and rotating it, you instead, like you rotate the other way. You would see the velocity rotate. Okay? So, and that would come from basically this idea, where if you imagine sort of the position, you do some rotation by epsilon on this, and you take the time derivative of this, the rotation is not time dependent. So what you have is the rotation acting on the velocity of the particle. Okay? So this is the idea of saying that the new velocity is this. Okay. But what happens in that is that r dot wouldn't change because r is not changing. All right. So the only thing in here that changes is theta. Does the Lagrangian depend on theta? No. So if the other stuff stays the same, then the Lagrangian will stay the same. And if the Lagrangian stays the same under a transformation, then we know the action has to stay the same. So we'd just be integrating the same thing. Okay? So this system is invariant under 2D rotations.
If a rotation or transformation is performed, does that not change the bounds on the integration of the Lagrangian as well?
So we're not changing the time.
Okay.
Because this is an integral over time.
Mm-hmm.
And what physicists usually do is just think of it as integrating over all time. Even though I introduced it as like a fixed interval,
Mm-hmm.
physicists don't really care about doing stuff properly, especially with limits and integration. So we just think of it as we're considering all time. Okay. Incidentally, and hopefully we can make this connection a bit more later, the Lagrangian does not depend on theta, which means that theta is a cyclic coordinate. And what we know about that theta is cyclic, well, what does it mean?
It means that as you change it, the Lagrangian does not.
Right, but what was the consequence of having a cyclic coordinate? Lagrange equations.
It doesn't appear in the Euler-Lagrange equation.
Yeah, so this is 0. And what is this?
That's proportional to the force, or equal to it.
Yeah, but specifically it's it's the time derivative of the conjugate momentum.
Oh, okay.
So if you have a cyclic coordinate, the conjugate momentum to that coordinate will be conserved because its time derivative is 0. So what that means is that this p theta is conserved. Okay, so let's see what is p theta. Well, so by definition, it's this, dl by d theta dot. This is the Lagrangian. What is dl by d theta dot?
P theta.
I mean, but from this specifically.
It will be mr squared theta dot.
Yeah. Okay. Does mr squared sound familiar?
Yeah.
What is it?
It's moment of inertia.
Yeah.
Of inertia.
So moment of inertia or rotational inertia?
Mm-hmm. So that.
Yeah, go ahead.
So that just relates the equation for the conservation of angular momentum.
Yeah, exactly. This p theta is, so mr squared is I. Theta dot is the angular velocity, which is omega. So you can see that this is the angular momentum. So we have this situation where the Lagrangian was invariant under rotations, and then seemingly relatedly, the angular momentum was conserved. Okay, so that is clear in this example because the parameter that describes your symmetry transformation, so that's theta, or at least the one that is kind of affected by it, and is the only one affected by it. Because it was a cyclic coordinate, it doesn't affect the Lagrangian. Then we can see immediately that we get this conserved quantity. Okay?
So would you see this example as a confirmation of the validity of the Lagrangian, or rather a confirmation of the validity of conservation of angular momentum?
Depends how you want to look at it.
I
Right?
guess the latter, but I don't know if I would view it as a confirmation of anything besides what I'm going to introduce later. I mean, you know this is true because
Deep dive said so.
yeah, but it's also basically just telling you, if you go through the Euler-Lagrange equations that if your system has no potential energy, then there are no forces. Okay? So what it's saying then is that in that situation, angular momentum is conserved. I guess it's like reassuring if you're just learning Lagrangian mechanics, which you are. But yeah, I don't know if I would view it as a confirmation of either of those things specifically. Remember, Lagrangian mechanics was designed to fit classical physics. We made it so that the Euler-Lagrange equations were Newton's second law. So the only thing that could change that is if the math changed, and hopefully it doesn't. Okay. So this is sort of a motivating example, but there's something a bit deeper that I want to talk about. So we want to talk about specifically, I can use other stuff. how's that? Continuous symmetry. That's what we want to use. So these are transformations that preserve the action. And for us, what we usually want is that they preserve the Lagrangian. But there's a sort of continuous set of these transformations. So we can describe this set of transformations. So for example, 2D rotations. By continuous parameters. And moreover, what we usually want is that, so what I'm saying is that for like 2D rotations, the actual rotation is given by this parameter theta, which is the angle that we want to rotate by. So this is the continuous parameter I'm talking about. And then what we also want is that if we compound these transformations, then what we should get is the transformation given by the sum of these two parameters. So this doesn't have to be the case, but I think it's always such that we can make it the case. We can choose a parameter that's like that. Okay. And we should be able to do this for all the real numbers that get put for this parameter. For rotations, it would sort of repeat after every 2 pi. Right. So yeah. Moreover, what we usually want is for these symmetries to have a notion of smoothness, so that we can do them for a sort of infinitesimal parameter, and then have this idea of like a difference between them. So basically having like a derivative of this transformation with respect to the parameter. So something like this should exist. So if we have a set of transformations, and you have, one transformation for theta, and then another one for theta plus d theta, these should be sufficiently close in a way that you could recognize as linear. Okay? So kind of the size of the difference of this transformation should be modulated by d theta. So yeah. So you sort of view these as functions. And subtracting them in this sense would be, if you put like a vector into here, you'd be subtracting, so let's say like this. So you'd be subtracting the resulting vectors. So if you have, this is the original vector, this is one rotation, this is a very close rotation, the length of the difference in those two should be somehow related. So I'll call this new transformation capital X. Yeah. Or sorry, I don't think it actually depends on. It depends on the group. But let's say for this example, this new transformation doesn't depend on what you originally transformed, but the size of it gets modulated by this d theta. Okay, basically what I'm trying to say is that this this set of transformations, it forms some sort of space that you can kind of put coordinates on, and those coordinates are the parameters you use to define the elements of the transformation. And then it has this notion of like those coordinates being smooth, or sort of smoothly patched together.
Almost like an equipotential surface?
Kind of. So, when I'm talking about specifically, I don't want to use like, advanced terminology, but, this is like a symmetry group, and then the idea of this sort of being continuous is that the group forms a manifold, and the idea of a manifold is that it's something that you can, in like patches of it, put coordinates on, and then the sense in which you put coordinates on it is sort of smooth in a way. So that if you have like two intersecting patches, you have two different ways of putting coordinates on them. That gives you like a function from your one coordinate space to another coordinate space, and that is smooth. Okay, so there's a lot of differential geometry, but I don't want to go too much into it. Regardless, the idea here is that, well, first of all, actually I can do a bit more with this. I said this is true, right? So this R of theta plus d theta is R of d theta, and we compose that with R of theta, and we're subtracting R of theta, and this all acts on x, right? But we're going to say for now it doesn't really matter which particular thing we're rotating. Okay. Well, this is actually I wanted to put the order. Well, this is R of theta composed with this transformation that is R of d theta minus the identity, right? You can also consider that as the rotation by 0 degrees. So the identity transformation is a transformation that does nothing. And what's basically going on here is that this is the derivative of this transformation when you're at the identity, and then its size is basically scaled down by this d theta. It's probably not visible on the phone, is it?
No, it's not.
Okay, what's the last thing that is?
The line above it is visible, so
Okay.
all you need is R theta composed of dr d theta of.
Okay. Oh, sorry, I just wrote it. Oh my god. So theta equals 0 is where the identity transformation is, because we're rotating by 0 degrees, or 0 radians there. And then this is scaled by d theta. And this thing is what x would be. That transformation I was talking about. Okay. Perhaps a more intuitive idea is that using this property, that composing these two transformations corresponds to this one transformation, but the parameters are added together. What we can do then is think of starting at this sort of identity transformation and then building up all of our symmetry transformations by doing the transformation by d theta and then sort of just repeatedly doing that, compounding those over and over until we get all the transformations for all of the theta. Okay? So you can think of the sort of infinitesimal transformation as this identity transformation plus d theta times this x transformation. Okay, I wanted to note that, oh, wait, never mind. Yeah, this is right. Okay. So d theta, it's this infinitesimal, and the typical idea with infinitesimals is that they're so small that if we just add them one after another, we can generate pretty much any number we like. That's sort of an informal idea of infinitesimals. So, if we wanted to achieve sort of the rotation by any angle theta, what we could do based on this is repeat the rotation by theta over capital N, n is some integer, and then basically do that n times. Okay? So not forever, but just n times. And then we could make n arbitrarily large, so take it towards infinity. And so when we do that, we make this theta over n so small that this rotation would be given by this. Okay? So this one you could kind of think as like a Taylor expansion, because this is like the identity and then plus d theta times the first derivative, and then you could have the second derivative, but we're saying that d theta is so small that the d theta squared is pretty much 0. Okay, so back to this. Then we're saying that each of these would be like this. That would be this, because this d theta is theta over n. And we do that n times. So raising it to the nth power. And what I mean by taking this to the nth power is that I'm composing it with itself n times. And this is, yeah, and then we can do this with the limit of n going to infinity. Okay, how are you doing with this?
It's a lot to wrap your head around, but I'm getting the general gist of it.
Yeah, so the idea is that we're rotating by just very small amounts at a time. That's probably too much. And the end result, by doing all these little tiny rotations, is that we get one, substantial rotation. And then the intervals that we're rotating by, we just shrink smaller and smaller. Right? So it's kind of like doing an integral. Similar idea. Okay? Every time we do this tiny rotation, how we're transforming the position of this point is that in part we're doing nothing. But then the sort of infinitesimal change that happens is this d theta times this x transformation of the point. Okay. This would be a lot easier if you knew linear algebra. I think it would be less confusing. But this x we could represent with a matrix. And then I think it would make more sense. But I'm not doing that. So in this case, what we could think of as x doing is that if you start here on the x-axis, it lifts up your point just a bit, right? Well, the d theta x lifts it up just a bit. If you start on the y-axis, what x does is it pushes your point to the left. Okay? So for those of you who know linear algebra, what that would look like as a matrix is 0, 1, minus 1, 0. So this 1 down here is saying that you're moving up in the y-axis. The minus 1 here is saying that you're moving to the left in the x-axis. And the column is basically telling you where you started. So the first column is x-axis, second column is y-axis. Okay. So each time you rotate this little bit, this is what you're doing. And then you're doing it, enough times so that you get the whole rotation that you want. So this is this general idea with these continuous symmetries, that you can build them up by doing these infinitesimal symmetries. Okay, but this is actually quite important. Do you recognize this sort of limit? I maybe write it something else. Or even this.
It doesn't seem familiar. I could tell you what it is, but...
Oh, you could... Wait, what do you mean?
I mean, 1 over n, or 1 over n as n goes to infinity is 0. And then 1 to any power n is just itself. So it's an... I guess you could call it an identity limit.
There's a problem where your thinking would make sense if you had a finite number of products, or sort of a bounded number of products in the limit. But what you're doing is an infinite number of products as you take this limit.
Mm-hmm.
So, what's your name? Who's teaching BC now?
McFall.
McFall? Okay, McFall has failed you. So this is something that you should definitely know. This is one of the definitions for E. The idea is that even though the addition to 1 that you have is getting smaller and smaller, because you multiply that number with itself an increasing number of times, that change is meaningful. And so you get E.
That was a year ago.
And importantly, if you instead do this,
Yeah, we did.
x over n, then this is e to the x. Okay, this is not as inspiring as I thought it was going to be, since you don't recognize this.
It was on an equation sheet. I can tell you that.
Yeah.
What might help is that write this out, maybe like, you can use the binomial theorem, like expand it out, see what happens in the limit, and what you get is the power series for each of x.
Mhm.
Okay, it's a nice little exercise if you've never done it before. And it's not hard. Okay, so you can use this thing from real number stuff as a motivation to say that, well, this thing, the identity we can say is like 1. Then this x is like this transformation x. Or you can think about theta x rather. And so what you could call this then, if I can find it right there. What you can call this thing then is e to the power theta x. So we're raising e to the power of a transformation, which I'm sure is very weird for you.
Mhm.
But what it's really expressing is this sort of repeated multiplication, which is the composition of functions here, over some infinitesimal parameter. And what's important here is this fact, that these combine additively. So Josh was here, I talked about homomorphisms. This should look kind of familiar.
Mhm.
And the fact that we have this additive to multiplicative homomorphism should scream out at you if once you've gained some experience with these things, that you're going to see an exponential. That's exactly what exponential does. Okay. No time left? Awesome. So what's the point? This x tells you how to do infinitesimal transformations for the specific symmetry transformations that you're talking about. And another thing to note is that, this was an example where there was only one parameter that tells you what the elements of your symmetry transformations are. But that is not necessarily the case. We could have multiple ones. The simplest one is that if your action or Lagrangian, whatever, is invariant under 3D translations, then you have 3 parameters. So, you can think of that translation as a vector. You can translate by some amount in the x direction, translate by some amount in the y direction, and translate by some amount in the z direction. So if you think of a translation that's parameterized by this translation vector A, there are 3 real parameters to that. And so these sort of x transformations, which we call the generators of the symmetry group, we get 1 for each parameter. So x1 would be the derivative of this thing with respect to x. You can call it ax as well. Maybe I'll do that. So when you're at the identity, you get another one here, and then you get your last one. And then what you can do, notably because translations commute, doesn't matter what order you do a translation in, is that you can express an arbitrary translation, or let me not write it that way. through this. Okay, and you could also just write this as e to the a dot, this sort of vector of generators. Okay? So, it seems like Mr. G showed you the list of topics I wanted to cover.
Mm-hmm.
So the idea of this thing, that we have this sort of continuous set of symmetries, is what a Lie group is. These generators, the things that describe the infinitesimal transformations that then build up to give you these overall transformations, they are elements of the Lie algebra of that Lie group. Okay? So I don't have time now, really, but what we're going to do tomorrow is we're going to do these infinitesimal transformations, like that, on the trajectories, and then using the fact that that will preserve the action, we then get consequences from that. And specifically, what happens is that we'll be able to read off conserved quantities. Okay? I think that's it.